Hi everybody. Today's section is going to be on 8.8, and this is called a differential equation with non-constant coefficients. Okay, this will be our first time learning how to solve a differential equation that does not have constant coefficients, but it's a very specific type that we're going to learn a trick for. So definition: a Cauchy-Euler equation is a homogeneous linear differential equation Sorry, I spelled Cauchy wrong. It has a Y. I just fixed it. Linear differential equation of the form. So this is the form that we're going to see x to the nth derivative of y plus a1 x to the n minus 1 n minus first derivative of y plus a2 x to the n minus 2 n minus first derivative of y plus a n minus 1 times x and then y prime plus a n y equals 0. And x is going to be positive. Okay? So notice this does not have constant coefficients because of those x's that are attached. However, the x's are special. Notice that they occur to the same power as the derivative that we're doing. Okay? So that's exactly what we mean by a Cauchy-Euler equation. Okay, a Cauchy-Euler equation has powers of x that appear the way that they're written here. Also, there is something important to say that the a1 to an are all constants. Okay, all constants. Now, the strategy. So our strategy is going to be to do a special change of variables, but it will not be obvious what the result of this change of variables will be. So we will do the following. Change of variables. And the change of variables we're going to do is let x be e to the z. In other words, z is going to be our new independent variable. Z is our new independent variable. Now, it's not exactly obvious what's going to happen if we were to let x equal e to the z in a problem like this. However, the following lemma will answer that question. So lemma. Under the change of variables, x equals e to the z, x to the k, and then kth derivative of y with respect to k is equal to d times d minus 1 times d minus 2 all the way till d minus k plus 1 of y, where d is equal to the derivative with respect to z, our new variable. Okay, so this lemma tells us what happens with each of these pieces, right? Because if you look back in the Cauchy-Euler, that's what each of these is, right? We have an x to the n and then y to that power, right? And so what this is saying, or sorry, not y to that power, but that's a derivative. So what this is saying is that it's going to turn each one of those into what we have here. Okay? So how would it apply to the whole thing? So that is what the following theorem will tell us. All you have to do is repeat this idea. So given a Cauchy-Euler equation, x to the n d to the n y dxn plus a1 x to the n minus 1 d to the n minus 1 y over dx to the n minus 1 plus a n minus 1 x dy dx plus a n y equals 0, where x is greater than 0. And I'm going to call this star the change of variables x equals e to the z transforms star to the following. Okay, let's call this guy double star. It's going to be d minus 1. Oh, that doesn't look clear. d minus 1, d minus 2, all the way to d minus n plus 1, plus a1 d minus 1, all the way to d minus n plus 2, plus, and then we have an a n minus 1 d plus a n. So it's all of this times y is equal to 0. This might be hard to read, but the way that you want to think of this is here, this becomes, and there's n things here, right? So notice that there are n terms. Here there's n minus 1 terms. So there keeps being one less, and finally there's only one term here, and then there are 0 on the last one, okay? So the number of terms you have matches up to which derivative you're on. So if it's an nth order, you're going to start by going down n times. So this is the theorem, and this is going to be the theorem that unlocks how you do differential equations that are Cauchy-Euler. Okay, now it's important because this differential equation that you end up with at the end is something you can use previous methods to do, right? And so I want to write out the steps for this. So step 1. All right, let me just write steps for solving Cauchy-Euler equation. So step 1 is going to be substitute x equals e to the z using the theorem above. In other words, star is going to become star star, right? That's the point. First thing we're doing is we're using the theorem. Step 2, you're going to solve star star. Okay, so step 2 is going to be to solve star star. Remember, star star, I'll say using methods of 8.2, right? Because it is, I'll just say star star is of the form P of D y is equal to 0, right? So that means you can solve it because they're all going to have constant coefficients, okay? And when you do that, when you solve it, this will give you n linearly independent solutions. And those solutions are going to look like this. y1 of z, y2 of z, all the way to yn of z. And it's important for you to remember that you have a z here, not an x. And so there is a final step. Step 3 is going to be to replace z back with ln of x. I should have been a little more clear on this. Since x is equal to e to the z, that means that z is equal to the natural log of x. And so this is essentially you substituting back. You have to go back where you came from, right? So replace z equals ln of x, and so your answers are going to be y1 of ln of x, y2 of ln of x, all the way to yn of ln of x. And so what would your general solution be? Your solution would be c1 y1 of ln of x plus c2 y2 of ln of x plus all the way to cn yn of ln of x. Okay, now of course, the case that you're going to see the most is the second order case. I know we just did this whole thing assuming that we're doing nth order, but as you guys probably tell, this formula is pretty cumbersome here, but I want to show you at least what it looks like when you have second order only. So what we will usually see in this class, not that you'll never see anything bigger, but what we will usually see in this class is a second order Cauchy-Euler equation. And this guy looks like this, right? Second order looks like this. Okay, so that's what a second order Cauchy-Euler equation looks like, where A1 and A2 are constants. So then if you do x equals e, if you let x equal e to the z, if I call this star, star is going to become, by the theorem, so we're doing the easy case here, right? So the way that you read the theorem is first, you're going to have d times d minus 1. We have two of them. Plus, and then we have a1d and then we have plus a2. All of that of y is equal to 0. Where, don't forget, d is not with respect to x, but it's with respect to z. So this is the small second order case that we're going to be seeing most of all. Okay? We're going to see this all the time. Okay, so that's the method. Let's go ahead and try some examples so that we understand what we're talking about. So let's do an example here. I want us to solve x squared y double prime minus xy prime minus 8y is equal to 0, with x being positive. By the way, I haven't talked about this much, but the reason that we are using x being positive, or that we need x to be positive, is otherwise this substitution doesn't work, right? Because we know we're going to let x be e to the z, but that's only possible if x is positive, right? Because e to the z is always positive. Okay, so now look, because of that, and that, we know that this is Cauchy-Euler. That's the tip-off, okay? It's not constant coefficients, but it is Cauchy-Euler. So we're going to let, well, I have it already written here. We're going to let x equal e to the z. Okay? So then, what is our guy going to become? It's going to become d minus 1 minus d, because it says plus, but we have a minus there. And then we have a minus 8. All of that of y is equal to 0. Okay? So how do we solve this? We actually need to distribute this out. So doesn't this become d squared, and then a minus a d is minus 2d minus 8. All of that of y is equal to 0. And so that factors into d minus 4, d plus 2 of y is equal to 0. So what does that mean? That means that we can go ahead and write our solutions, right? Because this means that r is equal to negative 2 and r is equal to positive 4, right? They're real roots. And so we know that y1 of z is going to equal e to the negative 2z, and y2 of z is going to equal e to the 4z. But remember, now what we have to do is we have to replace z with ln of x. We need to put an ln of x where we see a z, right? So that we can change it back. And so what does this give us for our actual solutions as functions of x? y1 of x is going to be, well, if you replace that with ln of z, it's e to the negative 2, with ln of x, right? It's e to the negative 2 ln of x, which is the same as x to the negative 2. And the other one is y2 is equal to e to the 4 ln x, which is x to the 4th power. And so we're ready to write down our general solution. So the general solution is y of x is equal to c1 x to the negative 2 plus c2 x to the 4th. Okay, and that would be the general solution to the differential equation. Okay, hopefully that wasn't too difficult, right? We're just using one new trick with previous methods, right? So let's look at another example. We're going to solve the initial value problem. It's going to be x squared y double prime minus 3xy prime plus 13y is equal to 0. And I need some initial conditions. Y of 1 is equal to 2. Y prime of 1 is equal to negative 5. Okay, again, look at this, this, and this, right? That tells us that this is Cauchy-Euler. Once we know we're Cauchy-Euler, we know we're going to let x equal e to the z. And so, what does our differential equation become? We have a d times d minus 1 minus 3 times d plus 13. All of that times y is equal to 0. So this becomes d squared minus 4d plus 13 times y is equal to 0. Okay. Now we need to go ahead and solve, right? We got to use the quadratic formula because that thing does not factor. So it's going to be 4 plus or minus the square root of b squared minus 4ac. So that's going to be 16 minus, what is that, 52 all over 2. 16 minus 52 is negative 36. So this is 4 plus or minus root negative 36 all over 2, which is 4 plus or minus 6i over 2, which is 2 plus or minus 3i. Okay, so what does this mean? This means that y1 of z is equal to e squared cosine of 3z. E to the 2z, I apologize. Yeah, e to the 2z cosine of 3z, and y2 of z is equal to e to the 2z sine of 3z, right? This is what you do when you have imaginary numbers, okay? So of course, we do need to replace back. So this means that if you want to write them as functions of x, remember, z is equal to ln of x. And so when you replace it back, we know that when you have an e to the 2z, that's just going to become x squared. So it's x squared cosine of 3 ln x, and y2 of x. These are the two linearly independent solutions, right? The other one is going to be e to the, so that's going to be x squared sine of 3 ln x. Okay? And so our general solution, or our solution so far, I should say, y of x is equal to c1 x squared cosine of 3 ln x plus c2 x squared sine of 3 ln x. However, we do have an initial condition, right? We know that y of 1 is 2 and y prime of 1 is equal to negative 5. Okay? So let's go ahead and actually solve those let's go ahead and actually plug in those numbers, right? So first of all, if y of 1 is equal to 2, that means that we get the following. So we get 2 is equal to, if you plug in 1, then your natural log ends up being 0, right? And so your first guy, because you had a cosine of 0, is just 1, and your x squared is 1, so you get c1, and then your sine of 0 is 0, so you just get 2 is equal to c1. That's nice. And so if you now use the other condition, so what I really did, let me back up a bit. What I did was 2 is equal to y of 1, which is 0. And so that's, which is c1. So that's how I got that c1 was 2. Okay, now if I do the other one, what is y prime of x? If I take the derivative of the general solution that I wrote down before, I actually get the following. Using product rule, you could differentiate that and then plug in the number. I don't want to waste too much time right now, but I'll tell you guys what happens, okay? So if you set y prime of 1 equal to -5, and you also use the C1 that you got already, you end up getting that C2 is -3, okay? So after some, let me just say after some calculus here, right? Because you need to take a derivative. But just to speed things along, let me write out the general solution for you now. The general solution, or sorry, it's not the general, it's a particular solution, right? Because it's an initial value problem. 2x squared cosine of 3 ln x minus 3x squared, sine of 3 ln x, right? Okay, so this is our solution to the initial value problem. Let's do a more involved one, okay? What if we have a non-homogeneous? So remember, this is going to be a lot trickier, right? Because we need to combine this with some of the more advanced methods. So let me just say that note if our equation is not homogeneous, we can still use this method to find YC if the associated homogeneous equation is Cauchy-Euler. Okay, so we're going to do an example. We want to solve the following differential equation: x squared y double prime minus 3xy prime plus 4y is equal to x squared ln of x, where x is positive. So we look at this, it's a little scary looking, right? Because we've got a lot of x's in there. We know the left doesn't have constant coefficients. But remember, guys, the first thing is always to find YC, and you do that by writing down the associated homogeneous equation, right? So what is the associated homogeneous equation? It's just x squared y double prime minus 3xy prime plus 4y is equal to 0. And now, and x is still positive. So what we have here is Cauchy-Euler. Okay, so this is important, right? It wasn't Cauchy-Euler before because we didn't have a 0, but now it is, right? So we can do the exact same trick that we did before. We're going to let x equal e to the z. And so this guy, the associated homogeneous equation, becomes what? It becomes d times d minus 1 minus 3d plus 4 y is equal to 0, okay? This is the same as d squared minus 4d plus 4 y is equal to 0, or d minus 2 squared times y is equal to 0. So this is a repeated root multiplicity of 2, right? And so what this means is our two solutions, y1 of z is equal to e to the 2z, and y2 of z is equal to z e to the 2z. But remember, you now replace it back because we know that z is equal to the natural log of x. And so we're ready to write down, let's just go ahead and jump to our YC, okay? Our yc, remember, is going to equal c1. What's e to the 2z, though? If you replace it with ln of x, is just x squared plus, and then the other one is also an x squared, but it's got an ln of x there as well. So I'm going to write it this way, x squared ln x, just to put it in the other order. Okay? Sorry, I forgot the c2. It's c2 x squared ln x. So this right here is our yc. Okay? Now what? Well, now we have to solve solve the other side, okay? We have to find yp. So now we find yp. Okay? So we have two methods of choosing here, okay? But I'm going to go with variation of parameters. There are two ways, though. What we could have done is we could have replaced our x squared ln of x and transformed that with x equals e to the z also. And we could have seen what became of that guy, okay? So that is one way to do it, but I'm going to use variation of parameters, okay? So I'm going to use variation of parameters. Now, it's easy to make a mistake here. However, there's something we have to worry about. So warning, this is kind of a subtle thing to overlook, but variation of parameters requires the coefficient of our highest order term to be 1. We have been calling this standard form. So what this means is I need to take my original differential equation and I need to divide the whole thing by x squared, right? Okay, because when we started out, we have an x squared in front, right? This guy right here, this x squared in front. And we're not allowed to have that for variation of parameters, okay? So what does our differential equation become, right? This is going to become, so dividing let me give it a name here, guys. I'm going to call it star. So dividing star by x squared yields the following: y double prime minus 3 over x y prime plus 4 over x squared y is equal to the natural log of x. Okay? And now it should be clear that this is our f of x, which is, by the way, easier than the f of x we would have got had we not done this, right? So remember, we set up our yp. We know that yp is going to be u1 x squared plus u2 times x squared ln of x. Where did I get this from? Remember, come back, yc is this, and all I'm doing is I'm taking the c1 and the c2 and I'm replacing it with u1 and u2. Again, this is from section 8.7, so everything we do here is section 8.7. In case you are confused, please go back and review that, right? So the idea is now that we need to find u1 and u2, okay? So remember, those have nice formulas attached to them, but first we need the Wronskian. So we start with the Wronskian, and I'm going to do the Wronskian of the two functions that we have, right? So the Wronskian of, what are our two functions? We have x squared, and then we have x squared ln of x. First we have x squared, then we have x, then we have x squared ln of x. The derivative of this guy is going to be the derivative of the first times the second plus the first times the derivative of the second. So that's just going to be plus x. And when we take the derivative of this, or sorry, when we take the determinant of this, let's see what we get. We get two x cubed ln x plus x cubed minus x cubed ln x. These two cancel out. We just get x cubed. So this is our Wronskian. Okay, we're going to use this in a second. Now, remember our formulas for u1 and u2. u1 is equal to negative y2 times f divided by w, right? This is what we have to take the integral of. So this is going to equal, let me see, what was y2? It was x squared ln of x, right? And then we have the f, which is another ln of x. So we have x squared and then ln of x squared, and then we have divided by x cubed, right? Because that was our Wronskian. But this is just ln of x squared divided by x, and this is an easy integral to do, right? We could just let u equal the natural log of x. Okay? So when we do that integral, what do we get? So if we let u equal the natural log of x, it's just 1/3 times the natural log of x cubed, right? Because it's going to be 1/3 u cubed. So this ends up being 1/3 times ln of x cubed. Okay? Oh, I forgot my negative sign, right? Sorry, that negative sign is there or there, so it's there. Okay, so it's negative of that. Now, what about u2? Remember, the formula for u2 is y1f divided by w without the negative. So what would y1 be? Remember, y1 was x squared. So it's going to be x squared, and then f is ln x, and then you're dividing by x cubed. So this one is just a single ln, right? Okay. What's this going to be? This is going to be 1/2 times the natural log of x squared. Okay. And so we've got our u2, we've got our u1, and this right here is our yp, and we have our yc on the other page, and so we're ready to write down our general solution. This means that y of x is equal to yc plus yp, which is going to equal c1 x squared, what was it, plus c2 x squared ln of x, plus, and then what was our, let me see, we have to do plus u1 times x squared, right? u1 times x squared plus u2 times x squared ln of x, right? Yeah. All of that is our general solution to the differential equation. By the way, you notice there's probably going to be some like terms here because, yeah, just looking at this, we actually have like terms here. In fact, this one and this one is a like term. So this ends up being, why not write it out in a nice way? I actually end up getting, let me see, this is minus 2 over 6 plus 3 over 6 is plus 1 over 6. So plus 1/6 x squared ln x cubed, because these are like terms, right? They both have an x squared and they also both have an ln of x cubed. So this is our simplified answer. Okay guys, hopefully the Cauchy-Euler equations are not too bad and just take some practice. Thanks very much for watching.